Okay, let's dive into the second part of our lecture series on the structure of the universe. Today we're going to talk about galaxies in particular, superclusters, filaments, and voids. Um, let's dive in here, kind of going back to where we left off last time, and just take another look, another quick gander at our place in the universe, at our place in the Milky Way. Remember, the lower estimate for the size of the Milky Way is around like 100,000 light years. It's probably bigger than that because we're stuck inside the darn thing. It's pretty hard to actually get a decent measurement of it. It took on this spiral shape. It probably wasn't originally a spiral. Um, it evolved over time, as all the galaxies have, probably only about 8.8, almost about 9 billion years ago. It started to look like it does today. And I know it doesn't look like the spiral, but we're stuck inside of it, right? When you're looking through it, if you take a gander at night, you'll see these real dark splotches, okay? That's just really dark clouds of gas and dust that are occluding your view all the way through. If you could look towards Sagittarius, the constellation Sagittarius, you'd be looking towards the center of our Milky Way galaxy. And it would be the brightest thing in the night sky. But there's so much stuff blocking our view that it's actually one of the darkest regions. It looks dark, even though it's the bright center of our own galaxy, just because there's so much stuff in the way. But still, the Milky Way is this beautiful band of stars goes across the night sky. Definitely take a look at it at night if you get a chance. We mentioned that we were a little ways out from the black hole at the center of our galaxy. We're kind of about halfway, maybe a little bit more or so. We're located in what's called the Orion arm of our galaxy. I think we might have mentioned that last time. It is in the region where we see the Orion constellation, and it's one of the arms of the spiral. So this is a top-down view, obviously a drawing. We don't have a picture of the real thing. It's a better zoom in on where we're at there. Woo, okay. So we can pinpoint ourselves in space pretty well. And that means we can pinpoint all the other objects around us and kind of know where things are and what's going on. So, like we said, it's probably got around about 300 billion stars. That's an estimate. So when we're talking about things like how much life is there in the universe, right? Remember, this is one galaxy with like 300 billion stars. Probably many more planets than that, if each star at least has a few. Right? And it's one galaxy among billions upon billions of tens of billions that are in the observable universe. Like, it seems almost impossible, like Carl Sagan said, that life doesn't exist somewhere else in the universe. Now, somewhere else in the universe is a big far cry from anywhere near enough to us that we could even have a communication or even get a communication. So when we're talking about searching for life outside of the Earth, a lot of the time we're talking about in the Milky Way. Like we want to find an intelligent alien civilization in the Milky Way. Like that's a feasible goal, right? But outside of the Milky Way galaxy, that becomes pretty difficult. It's a pretty tall order, right? Yeah, John. Uh-huh. Yeah, would evolution proceed the same way? Man, that is such a tough question, right? So many people have pondered on that and came up with their ideas about it. You could find just about every opinion in the world about that. The simple fact is we only have one example of how life has progressed anywhere, and it's here. And we know that's too small of a sample size to draw any conclusions, but it's fun to think about. Like, if you've got a different size planet, right? A smaller planet or a larger planet, you've got different gravity. So, like, how is life going to take advantage of that? And, like, what would life look like on a planet like that? What's the leap from single-celled organisms that seem quite simple to construct in comparison to a large organism like ourselves or even a worm? Like, that's a huge leap from a bacteria to a worm. Is it easy for life to make that leap? Or is it just like most life anywhere in the universe is just these little microscopic single-celled things? Right? So that's a huge question, and we'd love to have that answer. The first step is, I'd say, getting to Mars and finding microscopic life on Mars. That would be a huge first step. And it's a race now. Let's not kid ourselves. It's an honest-to-God space race because the Chinese just landed. Their craft just made orbit. I don't know if it's landed yet to Martian orbit, and they're going to land a rover or something like that on Mars and be driving around too. Our next one's getting there pretty soon. It's going to actually have a little. It's got the first ever aerial vehicle that's going to be on Mars. So it's going to basically have a little drone that can fly around and scout out like areas of the Martian surface for the rover to drive. Super cool stuff. Like, it just seems so sci-fi, but like being here on Earth and seeing all this technology that we have, it's like, why don't we use this stuff? Why don't we have it on Mars to explore? I'd say within your lifetimes, you're going to have a pretty good idea of whether or not life ever existed on the Martian planet. Like, there's a really good chance you'll have an idea because of all the stuff we're sending up there. So it's pretty exciting, but we'll talk more about that as we go. I like to couch most of the stuff we talk about in terms of life because that's a huge question, and we'll try and answer that near the end of the semester some. So we're somewhere around about halfway, maybe a little more, a little less, out from the center of the galaxy, stuck in this thing called the Orion Arm. Okay, so this is round about kind of where we last stopped talking. We were talking about our local group. Okay, so we're in one galaxy among like roughly 52 other galaxies, all clustered around these two large spirals, and we're one of them, the Milky Way and the Andromeda galaxy. And you kind of see Andromeda off in the distance in the picture there. The smaller galaxies are kind of orbiting around about the bigger ones, and the bigger ones are kind of orbiting around about each other. And we are on a collision course with Andromeda. Like, we will collide with them if things keep going the way they are, and there's no reason to suggest that they won't. But we're moving at about 123 kilometers per second. That's fast towards each other. But we're really far away, okay? So we're 2.2 million light years apart. We don't need to worry about this, right? The sun's going to be gone. Unless humans travel somewhere else in the galaxy, this is like the least of our concerns, right? Because we're a long ways away from any kind of collision. But mergers happen. We know that for a fact. The local group began forming about 13.2 billion years ago. Okay, given that the universe itself is only about 14 billion years old, our galaxy group, we're an old group. Like, our galaxy itself is pretty old. So it's kind of interesting to sort of think about that. Ooh. So Laniakea, and I had you guys look this up. This is the supercluster that we're a part of, and this is a tremendous scientific achievement for us to discover this thing. It's kind of on the order of deciphering that we're actually in the Milky Way galaxy, because we're in it, right? We're in this thing, and deciphering that we're in it was kind of a similar sort of a leap. We knew that superclusters existed. We knew we probably were part of one. But how do you map that out? You've got to map out the motions of like billions of galaxies to try and map that out and see how they're moving and what are they orbiting about. And then we can start to kind of put together a bigger picture of that. So we're looking at about 300 to 500 galaxy clusters, so individual local groups that make up this thing. So we're talking about somewhere like 100,000 other nearby galaxies. We're looking at 520 million light years across. This thing has the mass of about 100,000 times that of our galaxy. Like, if we take it all together, it's a big bunch of mass in a small area of the universe. So superclusters are kind of unlike local groups, and we'll talk more about this as we go. But superclusters are expanding with the rest of the universe. It's just that right now, temporarily, stuff is close enough together that it's kind of somewhat bound by each other's gravity. We're influenced by each other's gravity in this big supercluster. Our local group is not being pushed apart by the expanding universe. We are definitely bound gravitationally. And we'll talk more about gravitational expansion and all this stuff later on, but the universe is expanding, and eventually superclusters are going to spread apart. Okay, they are spreading apart. Right? So that's our supercluster. I want to show you if I can get this to work here. This is a quick view of Laniakea, which means like great heavens or something like that. It's a Hawaiian word. If any of you guys look that up, it's kind of cool. This is a quick view of that.
Somewhere in the universe is a small blue planet, the third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black, and a neighbouring structure, Perseus Pisces, in red. Scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
So that's pretty beautiful. Like when you look at the actual picture of that, like it really is beautiful, the picture that they created out of all that. It's not what it really looks like. Those little lines on there were tracing the flows that the galaxies are taking towards that great attractor or away from it. But it kind of defines like what our home region is, what our supercluster is. It was not that long ago that I used to teach that our supercluster was the Virgo supercluster. But now we know that it's just a tiny piece of this much bigger thing that we now call Laniakea. It's cool how quickly this stuff has changed in just the last few years even. So in that video, they said that the Laniakea was the supercluster those are the largest structures that we talk about. But sometimes we talk about in terms of the combination of those structures as the largest um, thing in our galaxy, in our universe, and we call those filaments and voids. Okay, and that's exactly what they were talking about that in the video. It's exactly what you guys saw just the other day when we did that activity with the histogram. We tried to figure out, are there empty spaces and are there spaces that are packed with galaxies anywhere out in space? And there certainly are. And this is a computer simulation, so it's not a picture, but it's made from real data. So what you're seeing is all of these filaments here, all these tiny little red lines, are just galaxies upon galaxies upon galaxies in little strings, like kind of connected together in these superclusters. And then regions where they come together, there's these humongous nodes, big clusters where there's lots and lots of galaxies together. And in between this crazy mesh, there's this area, this black area, where there's just not really anything. So it's weird that space is like this. Right? But this is the biggest structure we can see in the whole universe. This is like on the biggest scale that we can zoom out to today, this is it. Maybe there's some more structure other than that. Maybe you zoom out again, another level out, and the whole thing looks like a big spiral disk. Right? We don't know, but there's pretty good reason to accept that this is as far out as you can go. And still, like this is how the universe looks on all scales. But how many times have we had our world shocked, right? From thinking the Earth was the whole center of the entire universe to suddenly realizing that we're just going around the sun, and that's just one star system among many in this bigger thing called the Milky Way, and that's just one galaxy in the universe among billions of other galaxies, right? Which are parts of superclusters. So we have learned an awful lot. I want to turn back again, though, to look back time. We started off this whole presentation talking about this, the first presentation, but let's go over it again because some really weird stuff comes out of this. And it's going to come back when we talk about things like time. So you kind of have to understand enough about this to understand what we're saying when we're giving you the distance to something, like how big something is or how far away something is in the universe. You have to sort of understand this look back time. Most of the time, a lot of times there, when I give you a distance in light years, we are referring to look back time. Okay, and this is what I mean. So I'm just going to read you here. Since the distances between galaxies are always changing, it's actually easier to speak in terms of the amount of time it takes an object's light to reach us. Okay, so things are a little screwy because galaxies which are emitting the light are receding from us. They are flying away from us very rapidly. So by the time the light gets to us and we look at it and we go, oh yeah, that galaxy is X far away, it's not. It's really way, way farther away than what we can guess based on the light. So a lot of the time when we talk about the distance the light has traveled, not how far away the actual real true distance is much, much farther than the distance the light has traveled when it got to us. It's kind of a hard concept to grapple with. But that's what look-back time is. And if you wanted to calculate it, it's the difference between the current age of the universe and whatever the age of the universe was when the light left that object towards us on its path to us. And in the time since then, the objects move further away from us. So this doesn't really make any difference for things that are nearby. When we talk about our nearest star, Alpha Centauri, 4.2 light years away, it's not moving away from us. So like 4.2 light years is its actual real distance as well as its look back time. Okay? But because of expansion, distant objects are really much farther away than the distances we're giving you. Okay? So if, like I said, if galaxies didn't move, look back time would be a direct measurement of the distance, like in light years. Okay? The maximum look-back time is called the cosmic horizon, and it is related to the age of the universe. Let's take a look at what that looks like. This is a tough concept, right? I'm not going to quiz you heavily over this, but I want you to at least get an experience with it, because part of the fun about talking about all this stuff is that it messes with your head a little bit when you try and take it all in. And this is one of those things that you can look at time and time again, and every time you look at it, you're like, geez, how is that? How, right? So let me try and explain it to you here, okay? So there is this thing called the visible universe, which is the universe that we can see, okay? It's dependent on how long light has been traveling through space to get to us. But the universe is actually much, much larger than that. In fact, the universe is infinite. Okay? So there is light out there and objects making that light that's still traveling to us that hasn't even got here yet. So we don't even see those objects yet because it's still on its way. Whew, think about that for a second. So in terms of this picture here, if we pretend the universe is static and is not expanding, even with that, we can only see so far. Our home universe is right in the middle of this. Milky Way's dead center of this picture. We can see all the way out to the edge of what we call the visible universe. Okay? And I wrote there, in a static universe, the distance in light years to that horizon there is the same as the age of the universe. Okay? Any galaxy that's beyond that, its light still hasn't got to us. Like you see the little wiggly lines there. It's traveling towards us. So some questions ought to come to mind, right? First of all, like, as the universe ages, does that mean we see more galaxies that weren't there to begin with? Oh, the answer's kind of weird. Yes, kind of at first. So right now in the current age of the universe and the rate at which it's expanding, light is getting to us. So there's light on its way. Okay. At some point, expansion will be going so fast that distant galaxies will start fading from view and we won't even be able to see them anymore. So our cosmic horizon will actually shrink. Right now, the cosmic horizon's growing, like how much we can see, how far apart it is. But eventually, at some point, and we have a pretty good estimate of when that'll happen, we will see less and less. Here's another picture of the same thing. So if you're trying to draw one of these, either one of these is totally fine. Yeah, John. Yeah, that is a tough question. Up until just recently, we thought it was pretty constant. Most recently, we've discovered that the universe is actually accelerating. Yeah, how? Well, this stuff called dark energy that nobody really knows what it is. There's a lot of things in astronomy. You'll hear us refer to them as dark, like the dark side of the moon. It's not really dark, we just can't see it, right? Or we'll talk about dark matter. Well, it's matter, we just don't know what it is. Or we'll talk about dark energy. It's energy, we just don't know what it is. It's not that it's like black or something, it's like dark. It's just we can't see it, we don't know what it is. So whenever you hear that word dark in astronomy, that's kind of what we're saying. But yeah, the most recent evidence that we'll discuss later on, the universe is accelerating. Yeah, expansion's accelerating. Now, remember, I'll say this again, I've said it a bunch. Our local group, all those galaxies, Milky Way, Andromeda, all the ones that are local, they're not getting farther apart. Like, not because the universe is expanding. Out beyond that, we are getting farther apart from everything else. Okay, but gravity's too strong in our local group. Okay, so you don't have to worry about, are the atoms in my body expanding? Are they getting farther apart? Am I going to be torn apart? No, the gravity's holding you together just fine. Electromagnetic force is holding you together just how it should. Okay, but out beyond our local group, that's not the case. So another picture of the same thing. Now, this is another weird concept. Okay, so our present cosmic light horizon is 93.2 billion light years in diameter. Okay, the universe itself is only about 14 billion years old. So if you do the math there, our diameter ought to be 28 billion light years. We ought to be able to see about 14 billion light years in every direction from our Milky Way. But we can see a whole lot more than that. What we see is 93.2 billion light years in diameter. Okay, so that is directly related to the fact that the universe is expanding. If it wasn't expanding, the age of the universe would match how far we can see, and it doesn't. So when people say, is there any evidence the universe is expanding? Oh my goodness, there is gobs and gobs of evidence. In fact, it's the only way we can currently explain what we see. So there's regions like these little spiral galaxies out here where the light's on its way to us. The light is maybe within our visible galaxy, within what kind of is the sphere of our present light horizon, but it still hasn't reached us yet. Right? It's a real weird concept. Okay, everybody have that? Need a second? Okay, if you're trying to draw that picture, I don't care how you try and draw it on there. I think that was a question on your packet. It's a pretty simple picture to draw, though. Okay, let's keep going in with the observable universe here. So, in principle, how far can we see? Well, if you think about the Big Bang, which we're going to talk about some more, the universe was born in this very hot, energy-rich state. You couldn't see through it. So no matter what, there's a limit on how far back into time you can see, because you can only see so far back into time at the point at which light could travel freely through the universe. Yeah, there was a point when energy was so dense and thick, if you want to think of it that way, that light couldn't even travel. Like, that's hot, right? So we could basically see up to this point in time where light could move freely, which is known as photon decoupling. Don't get hung up on that word. Usually I'll refer to it as recombination. It's when electrons basically decided to go back to their atoms. So light was able to travel freely. So this is the universe at about like 91.4 billion light years in diameter right now. Okay, it's expanding. So because of expansion, objects that emitted light when they were close together are now a lot further apart. And that's why, like I just said, the observable universe is so much larger. What we can see is so much bigger than 2 times the age of the universe. Because 13.8 times 2 is not anywhere near 91.4. Okay, so as time passes, what we observe, our observable universe gets bigger. We can see further, like distance-wise. We're still seeing the same stuff, but it's further and further away. So since the expansion is accelerating, though, eventually objects will be moving so fast that their light's going to be redshifted beyond what we can detect with present technology or even future technology. Okay? At that point, they're going to move beyond the visible universe. So it's absolutely true, like, as the universe is getting bigger, we're going to see more stuff. Like, more light's going to reach us. Okay? But then we're going to surpass this point where the universe is expanding so fast that the farthest things away are going to start fading from view because they're going to be moving so fast away from us. Yeah, John? No. In fact, some of them right now are going almost the speed of light. Nothing. Yep, they'll keep going faster. So this is completely against every physics you've ever been told, because we've been told, we've been hammered into us, nothing can go faster than light, thank you, Einstein, right? And it's true. Anything that's moving can't go faster than the speed of light. But the weird thing is it's not the galaxies themselves that are moving. We're going to find this out later on. The galaxies kind of appear to be moving. They're not moving like there's little motors on them and they're like driving around, right? The space between the galaxies, this thing that we call space, is actually getting bigger. Think about that for a second. The galaxies, nothing gave the galaxies a shove and moved them outwards. The actual stuff that's between, whatever you want to call that stuff that we call space, emptiness, is getting bigger. And therefore, the gap between us is getting bigger. So run this through in your head real quick. If a galaxy's really, really far away from us, is it going to be moving faster or the same speed as one that's closer to us? Faster. There's more space between us and it. And if the space increases in size at the same rate, it's going to apparently move a lot faster. So the most distant things right now are moving at like, it's something like 90, 80 something percent the speed of light, which is insane when you think about it. But it really doesn't violate physics as much as we think it should. It really doesn't. This is some weird stuff. I love talking about it because later on tonight you'll lay down and you'll be laying in bed and you'll be going, oh my gosh, like there's galaxies moving at almost the speed of light, but they're not moving. It's the space between this getting bigger. Right? It's unimaginable that we can even figure this stuff out. It just blows my mind, right? There is an upper limit for how big this observable universe is going to get. Roughly at about, and this is just a calculation with physics, at about 124 light years. Currently we're at 91.4, okay? Oh, I think I meant to put billion there. 124 billion light years. That's going to be the point at which things are moving so fast they're going to start fading from view at the most distant things. Okay, we're not going to look over and see like a nearby star disappear, but like the most distant objects are going to start getting so dim we can't see them anymore because they're going to be moving close to the speed of light. Whew. Okay, one more picture to try and help you grapple with this. I put a lot of pictures in here because like, the only way I can understand this in my head is to see a visual of what's going on. So I think the more visuals you see, the closer you come to an understanding. This one's a little hard to grapple with. If you start at the top and work down, this is working from 8 billion years ago to 4 billion years ago to present day. So we're getting closer to present day, and we start out with 2 galaxies. Okay, this is not something close, it's something far. So don't think Andromeda, think something really far away, in another supercluster somewhere. We've got the Milky Way on the left in a distant galaxy. It is receding from us due to expansion. The space is getting bigger in between. And if you look at the ruler as we go down, our cosmic ruler here, the ruler is getting stretched out. See the ruler getting stretched out? Not the galaxy, the ruler. And so the light gets emitted. It's traveling at the speed of light towards us. However, the object that emitted it is traveling away from us, and we're traveling away from that object. So the light's like trying to catch us, but we're moving away, okay? So the proper distance in the next picture is going to be the distance to the actual galaxy, the actual true distance, what we would call the co-moving distance, okay? The distance that we usually give in light years, the look-back time, is the time when the light just left. So that was in the first picture. So in the second picture at 4 billion years, the look-back time is the point at which this light that's now hitting us left the original galaxy. Okay? But in reality, that galaxy could be much farther. It is much farther away. We've got to measure something, and we can figure this out. It's just whatever we want to talk about. So in a second, in the very last picture, this galaxy's far away. Its co-moving distance is like double the light travel look-back time to when that light was first emitted that's on its way to us, that hit us. Okay, question? So it's kind of 2 different things that we refer to. So if you hear the words co-moving distance, that would be the distance. You could measure it in light years or whatever you wanted to measure it in. But that's the actual physical distance between us and where that object should be right now because of expansion. And then the look-back time, which is what we almost always talk in, and you see like in the news or whatever, or on an article, is the distance from when the light left the object. So for things that are close by, like I keep going back to Alpha Centauri, and I'll link an article to that today. There was just a new discovery about Alpha Centauri. They discovered a new planet orbiting it, which is pretty cool. It's 4.2 light years away. That is the actual distance. It's not co-moved at all because of expansion. So we can measure things nearby. It's just that when things start to get really far, this starts to have a big effect on what we're looking at, right? It's a lot to take in. It really is. Okay, let's turn to something simpler now, okay? I wanted to mention this because somebody brought it up and wanted to know this question. So I put this in here. What's a constellation? Well, a constellation isn't anything special. It's just a group of stars that look a certain way that we pick out in the sky. Okay, so different peoples from all throughout history have named the constellations, right? They've named the Big Dipper the bear, right? They've named things like different than what we call them even. Okay, so the important concept though about constellations is that the stars that you see are actually, most of them are not nearby each other. They're very distant. So if we look at Orion, that you guys have probably seen Orion, Orion's belt, right? Betelgeuse. The actual stars in Orion, a lot of them aren't anywhere near each other in space. They just happen to be in that direction when we look. So keep that in mind when we're looking at how to measure distances. Like they look like they're right by each other, but they could be very different distances away from each other. Okay, it's just what we happen to see. So let's talk about Polaris. So Polaris is our North Star. It has not always been our North Star. It will not always be our North Star into the future. There will be different stars. At some points in time, there will be no North Star. This is a time-lapse photograph of looking towards the North Pole, and the stars make star trails as the Earth rotates on its axis. So if you think about a globe rotating on its axis, if we're looking up there towards the top of it, right? Anywhere there's a star out there in space is going to make a funny little circle, isn't it? Okay, the further the star is down away from the North Pole, the bigger the circle it makes. Every star makes a circle around the North. So if you do like a 4-hour exposure at night, you'll get all these cool star trails like this. Where's the North Star? It's almost perfectly in the center of all that. It does make a tiny little circle. It's just that you can't even see it. And the North Star is pretty faint compared to some of these other stars. But it would be right there smack dab in the center. So it is the North Star right now, but because Earth has another motion, we talked about how we rotate on our axis. Everybody's good with that. Day, night, right? We orbit around the sun. We revolve around the sun. So that's our year, right? One time around the sun. We also do this other funky thing called precessing. So the Earth's rotation on its axis isn't totally stable. It's kind of like a top. If you've ever spun up a top before on a desk, when it starts to slow down, it starts to wobble. It's like, okay? There's no friction on the Earth in space, so its wobble just keeps wobbling. So while we're spinning and going around the Earth, the sun, we rotate on our axis like this. We do this precessing motion. It takes a really long time, like something like 26,000 years or something to precess all the way around. Like it's not happening overnight. It's really long. It's very slow. But over a long enough time, the North Pole of the Earth points towards a different star or towards no star at all. So it's constantly changing as it rotates around like that. It's really kind of neat, huh? So in the past, like we know, like we can calculate backwards. Let's see, Earth's axis in AD 15,000 was pointing towards Vega. That was the North Star, right? Totally different star. And as we continue to do that, we'll point towards different things. Now, another interesting factoid is that we would precess even more drastically if the moon wasn't there. Luckily, we've got a big moon nearby, and it kind of keeps us from accidentally rolling all the way over on our axis occasionally. And we'll talk about screwed up seasons and maybe death to all life if the moon wasn't there, because we would have these huge climate swings as the Earth rotated around. If you're thinking about climate, yeah, precession has a role to play in ice ages and in warm periods. Okay, precession happens over the course of, tens of thousands of years, not over the course of, say, 100 years. So climate change right now is not related to precession. Okay, but yeah, it does have a role to play in ice ages and things. Whew, oh boy. All right, we're talking about a couple of more things here that are going to be important in the next lab that we do. Okay, so distance, the most important measurement astronomers make. That's a question on your packet. Distance. It's also one of the most difficult things astronomers measure. Seems like a strange thing to measure, but distance kind of tells us everything. It's the jumping off point to understanding everything else about the universe. So there's a lot of ways to measure distance. There you go. there's a lot of ways to measure distance, but there's really only one way that we measure distance like exactly without making any guesses, and it's called parallax. Okay, and it only works for things that are pretty nearby, and you need what's called a very long baseline for it to be accurate. So we kind of have a measuring stick, and we use the entire Earth's orbit to measure with. This is kind of weird. We're going to play with this down in lab. Here's how it works. You've all experienced this before. If you hold your finger out in front of you, and you close one eye, and you line it up with, like, say, somebody's head, and you leave your finger there, and you open and close the other eye, you'll see it shift back and forth. Okay? The amount it shifts by back and forth is parallax. Okay? Now, the further something is away from you, okay, there's going to be a difference in how much that shifts. In other words, the further the object is away from you, the parallax shift is going to be different. And if we know these values, we can figure out how far something is away. The Boy Scouts teach this in figuring out how far away it is to cross like a creek or something. You can actually do it right here on Earth, and we'll play with it down in lab. So you can jot that down for a definition there. It's the difference in the apparent position of an object viewed along two different lines of sight. The two lines of sight were your eyeballs, eyeball 1, eyeball 2. Okay, what's the baseline here? It's actually the distance between each eyeball, which isn't a very big baseline. Astronomers use the distance of the entire orbit of the Earth, one side of the sun to the other. It's a long line, so you get a big line of sight from either side. So that means you can measure farther. The bigger your baseline, the further you can measure. And like I said, this is the only direct way to measure a star's distance. It's akin to pulling a tape measure. A tape measure is a direct way to measure. Everything else is reliant on other numbers. This is direct. Everybody got it? Anybody need another second? I'm going to go too fast. Okay, here's a picture. Picture will really help out. So if you're trying to draw this, here's a picture right here. Okay, so what we've got here, and I gave you the formula. The formula is super crazy complicated. D equals 1 over P. Okay, it's a hard one there. D is distance. So what we're trying to do here is we're going to use the orbit around the sun to measure the distance to a star. Okay, and we're going to come up with a parallax number. Okay, P is the parallax in that formula right there. Okay, there we go, and an angle there. Okay, let me explain this for you here. So we've got the sun here. Okay, the Earth is going around the sun. The Earth's the blue dot. We have to make two measurements. One when we're on one side, say summer, and one when we're on the other, say winter. Okay, to measure a distance to a star, it takes a whole year. All right. So what we do is we make an angle measurement. How do we get an angle? We have to compare our star, which is the big one here, with some distant background stars. The background stars are so far away that they don't parallax. The farther an object is away, okay, the less it shifts back and forth when we open and close our eye. Okay, so if you get something that's so far away, it doesn't move at all. Needless to say, this is why the ancient Greeks thought the stars were all the same distance in a sphere, like holes were poked in the top of the sphere and light was shining through from the heavens. It's because they knew about parallax and they didn't see the stars moving back and forth, because it's a very, very small amount. Yeah, John? Yeah, you're right. It would be half a year. So yeah, we have to wait a half a year. Sorry. You're correct. We have to wait a half a year. So now let's plug in some stuff on this equation here. The one, okay, has to do with the fact that we're measuring in AUs, which are astronomical units, which is the distance from Earth to the sun. Because you're going to find out in this setup, we're going to be taking half of our baseline. And so that, since the distance from Earth to the sun all the way across to the next Earth is 2 astronomical units, half of that is 1 astronomical unit. So that's where this 1 comes from in this funny equation. Okay, P is going to be the parallax angle. And it's going to be given in what's known as seconds of arc. So we have to make this measurement. You could make it in virtually any sort of units. Like we could use degrees, or we could use radians, anything you can measure a circle with. So that's what parallax is measuring. It's in seconds of arc. The reason it's seconds of arc is it relates to making the units come out easy, and also you can measure something really small. This is much, much less than a degree. It's a really, really tiny amount that we're measuring. So back to my picture. On the far right of the picture, there's 1, 2, 3, 4, 5 stars back there. Well, there's the 2 with the white lines connecting them, okay? Those aren't background stars. That's showing you where our star would be viewed at against the background stars. So all we're doing is measuring the apparent shift in our star from the background stars as we go around the Earth, as the Earth goes around the sun. Okay, and we make a measurement, an angle. Okay, and you can see this angle here is going to be the same as this angle here. So we're trying to measure this parallax angle. Okay. Whew. So in lab, you're going to find yourself taking 1/2 of the big angle measurement, because when we do this in lab, you're going to get this angle down here from Earth, this angle over here from Earth. You're going to end up having to take half of this. So you'll see it'll be a little different when we do it in lab, but this is the general idea of how you do that. Okay, everybody good on that? Okay, so what about parallax? Well, it's really difficult to measure parallax accurately, partly because the stars wiggle such a little bit. Even with the entirety of Earth's orbit from one side to the other, right, half a year, you have a parallax of about 0.76 seconds of arc. That's our nearest star, not the sun. That's probably Alpha Centauri here. So the thickness of a piece of paper at arm's length, okay, is only about 30 seconds of arc. So that's like a fraction, only a serious fraction of the thickness of a sheet of paper that we're measuring. So it's no wonder the Greeks didn't think the stars were parallaxing. There's no way they could have seen it. Even with a telescope, it's pretty hard to see. Like, you need really sensitive equipment to pick this stuff up. So distances of greater than about 50 parsecs, or 160 light years, we can't measure them with parallax from Earth. So if a star is further than 160 light years, we can't measure it with this. Okay? Because when you look through the atmosphere, there's too much air, and it shimmers. And it shimmers enough that it fuzzes out the small amount that is moved. But if you stick something in orbit, like the Hipparchus satellite, which is up there, it's measured out to about 500 light years from Earth, because it's in orbit and it's not constrained by the light that can get in. But we're still using the distance Earth to the sun as a baseline. Okay, so that's pretty far. But we know the universe is a heck of a lot bigger than 500 light years, right? So how do we make those other measurements? Well, we're going to talk about that at another time, because they're considerably more difficult. But this is the base. This is the ruler. If we can make these measurements right, and we can come up with other ways of measuring that give us the same numbers as we know this exact measurement system does, we're confident. And we jump from one to the next to the next. It's known as the distance measurement, or the distance ladder. Okay, let's talk about the most distant things in the universe. Right now, unless it's changed, GNZ11 is the most distant object that we've observed. It was in 2016 they discovered this thing in Ursa Major. It's got a redshift, remember we just talked about that, of Z of 11.09. Yeah, Gab. Okay, let me back it up for you real quick. D equals 1 over P, okay? Distance equals 1 over parallax. Okay? Oh, now I'm jumping around a lot. See? There we go. D equals 1 over P. Okay, so this stands for the Goods North field of galaxies, is what it is, and its redshift number is 11, so that's where it gets its name. So this galaxy that you're seeing an actual picture of here, which is kind of pixelated crap, it would actually be bright blue because it's very, very hot and there's a lot of new stars in it. It's red because of expansion has shifted the red. It stretched the light out and made it red, shifted the blue into red. And we'll talk more about that later, but it wouldn't really look red like it does to us. If you could be right there, it would be quite blue. But this is the most distant thing we know of. It's somewhere around about 32 billion light years away. That's proper distance, okay? So like co-moving distance. We're observing it as it was about 13.4 billion light years ago. So its distance in terms of like relative distance when the light left was about 13.4 billion years ago. But its co-moving distance is 32 billion years. Whew. Okay. There's some weird things about this. This is only about 400 million years after the Big Bang. So it's like we were surprised because the Big Bang happened and then suddenly galaxies start popping up. Like for a galaxy to form this soon, it makes us question a lot of stuff. Like, is our current understanding of how galaxies form and how the Big Bang happened, is it correct? Because galaxies are forming way faster than we thought they would. Okay. But anyway, it's the most distant thing that we've yet observed. You want to jot that down? Here's a picture of sort of what that looks like in terms of, here's present day with the Hubble Space Telescope, which made the discovery. And then the Big Bang starting back here at about 13.77 billion years ago. By only 13.4 billion years, we've got this galaxy, GNZ11. It's like the first stars are forming, and we've got galaxies. We didn't think that that was really possible. So it calls into question a lot of our models of how the universe formed. And maybe as we find out more, maybe we'll find this is common. There were a lot of galaxies forming back then. Or maybe it was just a one-off weird oddball. It'd be strange that it was a one-off, because for us to discover it at all probably means that there's a lot of them, all right? Because it's hard to do. So that's GNZ11. I think I do have a little video of that here, okay? Let me see if I can pull that up. Anyway, it's not going to work for me. There we go. So, is it going to go now? There we go. So here's the Big Dipper. There's Ursa Major. Okay. If you zoom in, this is where this thing is located. Ooh, kind of a fly through here. Now we're in the Hubble Deep Field. So you see where they got that picture from, where they put that little montage together. And there's that little speck that's the most distant thing we've ever seen. Okay, so for that to exist, it does call into question a lot of stuff, right? So I'm going to leave you with this thought here. When we're thinking about Earth's cosmic address, we've got the Earth, right? And we walked through some of this stuff before. The solar system, the Milky Way, the local group, which is our cluster of galaxies, the Laniakea supercluster, where all those filaments are intersecting in our local region of space. And then if we want to jump outwards from there, we could describe the biggest structure that we have as all those filaments and voids, and that's what this block is depicting. It's like a block of space and time, and it's showing us all that filamentous structure of our universe. It's so cool that we can know that, right? Outwards from there, like the last thing you could say would be the observable universe. It's everything we can see, right? It's everything within our present light horizon. But that little cube there kind of really represents like what the universe looks like on the grandest of scales that humans have yet conceived of. Okay, so does anybody have any questions about any of those? Okay. You may have to do a little figuring to figure out how to do a little drawing there. You can do a little paint drawing and stick it in however you want. If you want to pull up a picture and paste it in, that's fine too. However you want to answer those picture questions. All right.